Hello everyone, today we are going to do section 6.1 Systems of Linear Equations, Matrices. We are going to start with a little review of systems of linear equations. What are systems? Systems are equations which considered together. For example, something like this. X plus 4y equals 14 and 3x minus 2y equals 0. Here we do have two equations and each has two unknowns. If you just give one equation, it's going to be hard to find solution. It's going to be a little bit too arbitrary. But two equations are going to usually give us one unique solution, but solution is going to be a pair of numbers, like 1x and 1y. So, two unknowns. How do we solve systems of equations? Well, there are many ways. For example, we can use substitution way to solve it, or we can use addition way to solve it. Some people like one way, some people like another way. I think in my worksheet, I used a substitution way to solve it, which we can use too. So for example, 3x equals 2y, from where we can solve it for y and get y equals 3x over 2. And then we substitute into the first equation and we get 3x over 2 instead of y multiplied by 4 plus x equals 14. 4 and 2 cancels, 2 here, and 6x plus x, 7x equals 14, from where x equals 2, right? And if I calculate y from my formula, if I plug in 2 here, it's 2 and 2 cancels, and y is going to be equal to 3. So solutions here is x equals 2, y equals 3. These two numbers supposed to satisfy both equations at the same time. So you plug them into first equation, it's becoming a true statement. You plug them into second equation, it's becoming a true statement. Okay? So usually substitution or addition works very good if you have 2-3 equations. But if number of your equations is going to be like 10,000 or 1 billion, it's going to be really hard and confusing to do the substitutions. Even labeling variables is going to be hard. So people developed a more organized way to solve systems of equations, and this way is involving matrices. So I'm going to start working with matrices. Usually step number 1 is to write down system of equation in a matrix form. What are matrices? In general, they are arrays of numbers, and usually they're kind of going to be like looking like tables. So here I'm going to create an augmented matrix. So first I'm going to copy coefficients of x, then coefficient of y, then coefficient of x again, coefficient of y together with minus 2, then put a little bar over here and copy my 14 and 0, then put them in square brackets, and this is called augmented matrix. Why it's called augmented? Augmented means enlarged. Generally speaking, the matrix of the system is going to be these four numbers. When we add the right side after the bar, we are going to enlarge the matrix, and that's why it's called augmented matrix. Okay, I'm going to label it. So it's augmented by the right side. Okay, so right now we are going to just practice in converting systems into matrices. So example number 1, I'm going to write down system of 3 equations. 2x plus 3y plus 4z equals 1. X plus z equals 2, and y plus 2z equals 3. I'm going to convert it into augmented matrix. I'm going to put my square brackets. I'm going to have 3 lines over here. Lines are called rows. And I'm going to copy the coefficients of x, y, and z for the first line. It's 2, 3, and 4. I'm going to put my bar and copy the right side. Close the square brackets. Here we do have x, but we don't have y. We are going to put 0 instead of y when we don't have the variable. Z coefficient is also 1, and we do have 2 on the right side. Here we don't have x, so we are going to put 0 for x, and 1 for y, and 2 for z, and 3 on the right side. So we just converted it. Okay, now how to convert augmented matrix back into the system? Well, let me erase something. For example, I'm going to erase the top. I want to have this example and that example together on the board, so I'm going to just erase the top. Imagine somebody gives us actually augmented matrix and they're asking, well, how the system was looking. And they are giving us 1, 3, 0, 9, and here 0 and 3. The system was looking like this. This was coefficient of x. So you write down x and you can put 1 in front or you just can forget about it. plus 3y equals, and the right side is 0. So this one comes instead of equal sign. 0x plus 9y equals 3. Well, usually people don't write it down this way, right? They are writing down x plus 3y equals 0 and 9y equals 3, right? And that's how the system is going to look, okay? What is interesting about matrices? Well, remember how we can add equations and subtract equations and kind of multiply equation by number. For example, I can take this equation, multiply both sides by 2, and the equation is not going to change, right? Or I can add these two equations together, and it's not going to add me more solutions, or we're not going to lose any solutions. Well, for matrices, these operations, which is similar to equations operations, are called row operations. And I'm going to describe several row operations which we are going to use in future and give you examples of how to use them. Again, row operations are stuff we were doing with equations when they were equations, but kind of, you know, just set as a row. So row operations. Number one, we can interchange any two rows. Interchange any two rows. Well, if you are working with a system of equations, that means that you take equation number 1 and put it as equation number 2 and equation number 2 as equation number 1. Everyone knows that it's not going to change anything, right? Change position of equations. So I'm going to put kind of comparison so you kind of understand why the rules are coming from there. What else we can do? With equations, we can multiply whole equation by non-zero number. We can do same with rows. Multiply equation by any non-zero number. It's like multiply the row by any non-zero number. It's multiply equation. Multiply equation. Multiply equation. We can do multiply equation too. Okay. Remember that when we multiply equation, we multiply the left side and the right side, right? Same over here. We multiply like whatever comes in front of the vertical bar and after 2. Row operation number 3, add or subtract rows or multiples of them. Well, we remember that we can add or subtract equations, right? We can do same with rows. Add or subtract rows or multiples of them. What does it mean? Well, just rows means that you take equation number 1 and add to equation number 2, right? Well, usually we do this when we do elimination, when we solve systems. Multiples. Well, sometimes you cannot eliminate anything by just adding two equations. You need to multiply one of them by, for example, 2 and then add it, and then it's going to eliminate. That's row operation, which is going to be addition or subtraction. Now I'm going to give you examples of row operations and kind of how it looks like on real equations. So I'm going to do the matrix here and the equation here, and I'm going to kind of tell you like example of what. So I'm going to start with example of first interchange of the rows. So I have my matrix 1, 3, 0, 9, 0, 3 here. What I'm going to do, I'm going to take row number 1 and put it instead of row number 2. And row number 2 instead of row number 1. So what matrix I'm going to have? 0, 9, 1, 3, 3, and 0 here. If I was using a system of equations, it would be looking like this. X plus 3y equals 0, right? And 9y equals 3, the system of equations. What is this? This is going to be what? 9y plus 3, oh, 9y equals 3, sorry. And x plus 3y equals 0. So this operation. So basically I changed position of the equation in the system. It's not going to change anything. Number 2, multiply equation by non-zero number or multiply a row by non-zero number? Well, I'm going to again return back to my matrix, original one. And for example, multiply the second row, this one, by negative 1 over 3. So what I'm going to get? I'm going to write down first. Row number 2 equals negative 1 over 3, row number 2. This is like old row number 2. This is new row number 2. So I'm copying row number 1, 1, 3, and multiplying each term here by negative 1 over 3. So 9 by negative 1 over 3 is going to give me minus 3. And 3 is going to give me minus 1. And 0 is going to still give me 0. Well, I did my operation. On a system of equations, how it's going to look? Well, it's going to look like I took this equation and multiplied it by negative 1 over 3 on the right side and on the left side. And I got equation minus 3y, and which is equal to negative 1. Which is exactly the same. So basically row operations are just what we were doing before with equations. Now add or subtract row or multiples of them. I'm going to kind of use this one. Imagine that somebody already modified equations and they're looking like this. 1, 3, 0, negative 3, 0, minus 1. So what I'm going to do, guys, I want to eliminate this 3. What I'm going to do, I'm going to do row number 1 equals row number 1 plus row number 2. Little ones are going to be like old rows, and this one is going to be new one. What is going to happen if I do this? 0 plus 1 is 1, minus 3 plus 3 is 0. This one is going to give me minus 1, and over here I'm going to just copy the row. Okay, so what I'm getting here is like third operation, add or subtract. I did not multiply this row number 2 by anything, but if you go back for original matrix, I actually multiplied it by negative 1 over 3. So kind of I combined these two operations together. I'm going to convert this system I got back to actually equation form. So what is this? That's x, right? 0y equals negative 1. 0x minus 3y equals negative 1. If I divide this row by negative 3, which I can always do by rule number 2, I'm going to get here 1, 0, negative 1. If I divide by negative 3, I'm going to get 0, 1, 1 over 3. So, well, basically, guys, instead of third equation, I'm going to have a solution. Y equals 1 over 3. You see what interesting fact I have over here. After doing all these row operations, I eventually got a matrix which is looking like a diagonal matrix. Well, it has different numbers here, but over here it's exactly diagonal matrix, has only numbers on diagonal, and these numbers are ones. Then my right side is going to be actually a set of solutions, x and y. So that's what we are planning to do with our matrices. We are going to work in this direction to just kind of see how it helps us to solve equations. Basically, you already seen, right? You take a matrix, you do these row operations, try to bring it to diagonal form with 1 and 1, and then you are going to have a solution here. Well, maybe I'll just going to explain next thing. Let's erase everything. Row operations is going to take too much space on the board. Okay, well, ideal solution, as we see already, is going to be something like this. 0, 1, 1, and A and B over here, which is going to mean for us that x equals A and y equals B, and this is solved. But sometimes it's too long to eliminate all possible like numbers here. Sometimes, guys, it's going to be not bad to bring it to the form something like this. I use D over here. No, I used C actually. Let me go together with my notes. So people who are using, This matrix is called diagonal because it has only diagonal elements, right? This matrix is called a triangular. Triangular means that everything below diagonal is 0, and that's upper triangular, and everything above the diagonal is non-zero, and you prefer to have ones on diagonal. This matrix is still not bad to solve system of equations because, for example, here we have y equals b, and you can take this y equals b and plug it into your first equation and have x plus c multiplied, it was y here, now I put b here, equals a, from where x equals a minus cb, which is not difficult to solve. Normally, guys, in future, we're not going to try to build a diagonal matrix. We will try to build upper triangular matrix and just solve backward equations like one above another one. You're not going to solve systems 5 by 5, but 2 by 2 and 3 by 3. Well, actually, the process over here is called Gaussian elimination. And the method works for large matrices too. Let's try to use it on 3 by 3 matrix, okay? Let me, maybe I erase this one. Well, if you represent matrix like a triangular one, it's called a row echelon form. Normally, it's supposed to have ones on diagonals. It can have anything on above diagonal and zeros below diagonal, okay? It's like not important right now why people call it this way. You're supposed to just remember that it's supposed to be upper triangle, okay? But mathematically it's called row echelon form. I'm going to give you next example, I think it's number 4, considering matrix 3 by 3 and solving actually using this method. Yeah, that's going to be a little bit long and boring. But I think that's the best I can do. I tried to not consider too many operations here. First, I'm going to convert it into augmented matrix. So it's 2, 2, 0, 6, 1, 1, 1, 1, 3, 4, minus 1, 13. I think I got this example from the book. I would not choose 13 as a number here. So, what I'm going to start with, I'm going to put my row, which consists out of ones, on the top. You will see why I'm doing this, but not right now. So I'm going to do interchange of row number 1 and row number 2. So my first step, 1, 1, 1. I have to kind of take the whole row, and then 2, 2, 0, 3, 4, negative 1, and that's a 6, and that's 13. Next operation I'm going to do is to eliminate these 2. My goal is to get all zeros below diagonal, right? So I need to eliminate 2, 3, and 4. How do I eliminate 2? Well, I can multiply my first row by 2 and subtract it from second row. So my row number 2 is going to be old row number 2 minus 2 row number 1. When I do this process, I'm not going to do anything with row number 1. Actually, I'm going to use it to modify row number 2. So 1 multiplied by 2 is going to be 2, subtracted here is 0. 1 multiplied by 2 is going to be 2, subtracted here is again 0. And 1 multiplied by 2 is 2, subtracted from here is going to be minus 2. Again, 1 by 2 is 2, multiplied by minus, it's going to give me 4 here. I'm going to copy my row number 3. You can do 2 operations at once, but I'm going to as example, I'm going to do only 1 operation. What I see, well, I'm closer to my diagonal form. What is going to be good? If I move my row number 2 instead of row number 3, if I exchange them. This way, I'll need to eliminate less numbers, because these 2 are already zeros. I'm going to just copy everything. So 3, 4, minus 1, 13, 0, 0, minus 2, 4. So you see that I'm almost done. Actually, I have almost diagonal matrix, except this 3 is bothering me a little bit. Now, what is going to be my next step? I'm going to take a row number 2 and subtract from it 3 row number 1. It's very nice when you have 1 over here, because you multiply by like something nice, natural numbers. 1, 1, 1. So I multiply 1 by 3 and subtract it, I'm going to get 0. 1 by 3 is 3, from 4, 1. 1 by 3 is 3, and minus 1 is minus 4. So 1 by 3 is 3, so I'm going to subtract it from 13, 10. And I'm just going to copy row number 2. I'm almost done, right? I'm just going to probably turn this into 1. How? I'll need to multiply row number 3 by negative 1/2, right? If I do this, this is going to turn into 1. Maybe I don't want to rewrite everything. I'm just going to kind of erase this. Put 1 here, and if I do multiplication of this by negative 1/2, I'm going to get negative 2 here. Well, now I have this diagonal form, triangular form, which is row echelon form. What I'm going to do next? I'm going to solve it back to get my solutions. So my z, which is my last coordinate, is already kind of solved, right? Z equals negative 2. If I just write down this equation, that z equals negative 2. I'm going to use z equals negative 2 substituted here. So it's y, 1y, right? Minus 4 by negative 2 is going to give me 8, and over here 10, from where y equals what? 2, 10 minus 8, right? Now I have 2, z and y. I'm going to plug them into my first equation. That's x, and then plus y, which is equal to my plus z, which is equal negative 2 minus 2 equals to 1. Well, I see that my x equals to 1, so I got my solution. My solution here is going to be x equals 1, y equals 2, and z equals negative 2. I solved the system. Well, let's consider special cases. What other ways can we kind of have if we solve system of equations? I don't want to erase anything from over here. On my worksheet, I just consider them separately, but here I just want to do some kind of changes over here. Imagine that you solve up to here, and you get something like this. Instead of 1, you get over here 0. Special case number 1. You have all zeros and there is a number here. If you write down this as equation, you are going to have that 0 multiplied by z equals negative 1. Can you make up z to multiplied by 0 and get negative 1? Well, you know that multiplied anything by 0 is going to give me 0, right? So this statement is impossible. Impossible means that the system which turns into matrix like this, or for which row echelon form looks like this, is going to have no solutions. No solutions. This is special case number 1. Okay? Okay, very good. Now, I don't want to, again, erase everything. I just want to modify my last step. Again, we can consider a system which brings you to a special case number 1, but it's much easier just to consider one matrix. Special case number 2. Let me erase correct solution. What if this one is 0? This one is 0. So you have 0 here and 0 here. Then equation we have from the third row is going to be 0z equals 0. And you look at this equation and you see that any z is going to fit here. Z equals 1, multiply by 0, get 0. Z equals 2, multiply by 0, get 0. So actually z is going to be a free parameter here, and you can set it up as t and say that t is any real number. Okay. Now you can use this z as a number and solve like we were solving before. So you write down second row, y minus 4, instead of z use t, equals 10, from where you can calculate that y equals 10 plus 4t. And the last one, x plus y, which is already 10 plus 4t, plus z, which is equal to t, equals 1, from where you can say that x is going to be equal minus 9 if you move this 10 together with 1, minus 5t. And your solution is going to look a little bit strange. It's going to have a free parameter t, for which you can use any number, and you are still going to get a solution. And, well, it happens sometimes, and usually it happens when you have something like this. The whole row equals to 0. Okay. And you say that t is any real number, special case. Okay? So now guys, I'm going to give you 3 problems to solve on your own, and of course I'm going to solve them myself too. And they are going to deal with these 3 cases. Case with unique solution when you have 1x, y, z, or 1x and y. Case where you have no solutions, and case where you can have infinitely many solutions depending on what you set for t. They are going to be very, very simple equations, and they're going to require very small amount of operations. Self-work. So A, x plus y equals 3, x plus 2y equals 5. My first system of equations. B, x plus y equals 3, and 2x plus 2y equals 1. And C, x plus y equals 3, 2x plus 2y equals 6. I'm going to count to 5 and solve it myself. And you can stop the video and try to do it on your own and compare our solutions. I'm asking you to not solve them as systems of equations, but use augmented matrices. It's going to be very easy to solve them as a system of equations. It's just like the goal of this section is to teach you how to use these augmented matrices and row operations. Okay, 1, 2, 3, 4, 5. I'm going to start solving problem A. So I'm going to write down augmented matrix. And, well, because it's just 2 by 2, I'll need to eliminate this 1, right? I'm just going to subtract row number 1 from row number 2. So row number 2 equals row number 2 minus row number 1. What kind of matrix I'm going to have? 1, 1, 3, 0, 1 here is going to give me 1, and 3 minus 5 is going to give me, 5 minus 3 is going to give me 2. Well, from here I do see that y equals 2. I plug it in over here and I have x plus 2 equals 3, from where x equals 1. So my solution in this case is going to be 1, 2. X equals 1 and y equals 2. Maybe I should use different parentheses. This looks like a set of numbers. It's actually supposed to be a pair of numbers. Okay, solution. B. 1, 1, 2, 2, 3, 1. Well, I'm going to do the very same operation to make it 0 because, no, I'll need to multiply by 2 actually. So R2 equals R2 old minus 2 R1. What I'm going to have? 1, 1, 3. Multiplying by 2 is going to give me 0 here. Multiplying by 2, subtracting 0 here. Multiplying by 2 is 6. Subtracting from 1, negative 5. You see what I have? 0y equals negative 5. Impossible. No solutions. You see? Just you cannot make a number here, multiply by 0 and get negative 5. And the last one is going to be the same augmented matrix, right? So I'm going to apply same operations. So just like this side is going to be different. 1, 1, 3, 2, 2, 6. If I do a very same operation, row 2 minus 2 row 1, I'm going to get the matrix, which is going to be 1, 1, 3, 0, 0, and 3 multiplied by 2 is 6. 6 minus 6 is 0. So I'm going to get my third case, all zeros, from where y is going to be equal to t, right? Because actually 0 multiplied by y is 0, works for any y. T is a real number. And now I just need to find x. I don't have any space here. I don't want to move anywhere. So it's x plus y, which is t equals 3, from where x equals 3 minus t. Well, what I'm going to do, guys, I'm going to circle my solution. This is part of my solution, and this is the second part. So usually you give x first, x equals 3 minus t, and then you write down y equals t, and then you write down that t is any real number. Okay, do your homework. I set up few 3 by 3 matrices. Most of the homework is 2 by 2. Try to use row 1 operations, okay? Okay, that's all. Thank you.